So on.
Hi team! Welcome to New Zealand National Biomechanics Day for 2019. So my name is Kim Hébert-Losier. I'm your host for today, coming to you live from the University of Waikato Adams Center for High Performance. So I am a senior biomechanics lecturer and researcher for the School of Health, Sport, and Human Performance, and we're really excited to have you today to explore what we do with biomechanics here. So we have 3 exciting stations coming up to you. If ever you have any questions, feel free to jump onto our live chat and ask some questions, and we have some biomechanical experts that are here to answer your question. So come in with me. So come on over. So mind the wires and the expensive equipment. Step into our lab. So welcome to our space. We are very fortunate here to be joined today by Aaron. Aaron has graciously accepted to be our model for today. He's a top sprinter and will be analyzed for you on our treadmill here. So we're very lucky to have an 8-system Qualisys 3D motion analysis system. And yeah, so he's already all set up and ready to go. So before we start though, we'd like to show you a quick video to show you about motion capture and what it's all about. Good. Just a second.
Motion capture has got an incredible future, and it is a marriage of performance, but it's also this incredible artistry. Oh, wow!
He wanted to get inside the character. He really wanted to fund it. He didn't want to just be a voice artist who came in after the fact and did words.
You get out of the and Helmet has a sort of Madonna type headset thing, which is actually a camera which comes to here. This camera is really weird because it's right in place. It's got a little circle of LED lights, so you're literally carrying around the actress's dream. You have your own little private keypad. It's really nice, but actually it's really weird. And then you kind of have to forget it and imagine yourself into a vast creature in a huge space when you're really crawling around on a great big carpet.
There will be head turns, there will be moments from that performance that you give that can be pulled out and extrapolated and will become part of the small clear.
Andy Serkis is unlike any other actor. He can inhabit characters that don't speak and emote in ways that you don't really see often in movies.
The basic usage of performance capture is, as you see it on screen, you will see names, but they're names which are infused with the heart and soul of an actor's performance.
You can be blinded by the technology and you find yourself weighed down by it. And I think Andy brings a spirit and an understanding and a simplicity. He's able to push the technology to one side and think about it in terms of just a real live action performance.
We're trying to break through in terms of technology that will, or methodology rather, that will help us break through into finding how we're going to anthropomorphize, how we can humanize.
Amp it up a little bit just to get it to breathe because the whole facial structure is so much larger than ours.
Smash.
technology yet for traditional character comics.
What are you saying, Jake? You knew this would happen?
And the technology, you can create the technology to make these things happen, but it's the actor that provides the soul. You use the word soul, and the technology ain't going to provide the soul. And that's where the performance captures the soul of the actor. That's what it's about.
So that was a quick introduction for you guys. Hopefully you've recognized a few of the movies or the actors in these movies. So that's actually where 3D biomechanics has come from. So it's originally from the gaming and animation industry to make things look more real. So here at the Adams Center for High Performance, we use the technology to inform on athletic motion and ability to help enhance performance and decrease risk of injury. So we're just going to do a quick switch around for the screen so you guys can follow along what we're doing here in the back. So we'll get Aaron to come back into the picture. Okay, so, all right. Okay, so as you can see here on the screen, this is actually in real time. So Aaron is moving around and the little dots on his body are getting tracked. So the way the system works is that the cameras that you see around the lab, they send out red light. Okay, we don't see the red light because it's not in the visual spectrum of light that the human eye can see. But the principle is the red light hits these reflective markers, which is the same material that you have on your sports clothing and gets reflected back to cars at night, for example. So the red light reflects off the markers, gets picked up by the cameras, and when there's two cameras that sees the same reflective light, it can reconstruct in three-dimensional space the precise location of the individual markers. So now if we know exactly where we're putting the markers and how they relate to the human body and human anatomy, we can then track the way that these markers move and reconstruct in 3D very accurately the way that Aaron is going to move. Okay, and just before he starts moving, just want to show you how this is a 3D space. So we can look at it however way we want. Okay, and then we can actually, here, create a virtual skeleton of Aaron. So Aaron, can you, he's kind of doing the Macarena now. And you can see that at a few instances, all of a sudden we lose some of the segments. Now, what do you think is going on? Any takers online? Okay, so for us to be able to reconstruct in three-dimensional space, the cameras need to pick up each one of the markers. So now if we happen to hide some of the markers, or the markers are invisible, then we lose the head. Okay, so it's very important that we arrange our camera system to be able to track all of these markers over time. Cool, let's get into some running.
We'll go 2022, 24.
Yes, sir. When Aaron is ready, we're going to collect some live data. speed, Aaron ran at 20, 22, and 24 kilometers per hour. Now he's maxed out our treadmill, okay? Our treadmill does not go faster than 24 kilometers per hour. Now kids, don't try this at home, okay? Because if it was me, I would have flown off the treadmill, okay? Now, take you through a little bit of what information we get. Okay, so this here is the information that we just collected. Okay, you can see how nice and clean it is and how we're able to track all of Aaron's movements. Okay, and we can turn this in 3D space. Okay, now this is the raw information. So this is kind of cool, but really it's what you do with the information that you collect that's even cooler. All right, so we'll pull out the reports. Okay, so you can see here, this is Aaron. This is his little reconstruction of his running trials. Okay, so we can build this little skeleton. Now, one important thing to note is that this is actually captured at 300 hertz. Okay, so 300 hertz means that we're collecting 300 images per second. Okay, so that's really fast. So now imagine if you're a coach trying to look at someone sprinting at 24 kilometers per hour on a treadmill. You can maybe pick up a few things. Okay, you can look at the way that they're hitting the ground. You can maybe look at their knee angles. You can look at, their arm, but you can't look at it all at the same time. And you definitely can't slow it down and really look step by step what's going on. So this provides you a really powerful tool to go back in time or to analyze human movement in really, really fine detail. Okay. And what's even better is that then you can actually put some numbers to what you're seeing. Okay, so we did this with Aaron. Aaron has been our subject here for National Biomechanics all day, so he's got his workout in, that's for sure. And you can see here, or hopefully you can, the 3 different speeds that he ran at. Okay, so we have 20 kilometers per hour, 22 kilometers per hour, and 24 kilometers per hour. Okay, now there's a few key things in running. Okay, so running speed, you can run faster mainly by relying on 2 main things. So step length. Okay, so how far you take for every step. Okay, so if you want to go faster, you need to take longer steps. Or step frequency. So now step frequency is how many steps you take per minute. Okay, so to go faster, you can also increase your step frequency. So take quicker steps. Okay, so you can increase step length, or you can increase step frequency, or you can do both at the same time. Okay, so if we first look here, when we increase in speed, we see that Aaron is increasing his step length, but he's also increasing his step frequency. So now at 24 kilometers per hour, he was taking 240 steps per minute. Now that's very fast. Okay, you have to move your legs really fast to be able to take 240 steps in 1 minute. And what we notice in Aaron is that we can see that he has actually a slight difference between his left side and his right side. Okay, at the fastest speed, his left step was about 7 centimeters longer than his right step. So we're always a little bit unbalanced. It's rare that we're perfectly symmetrical. So it's talking with Aaron about, okay, well, is that a problem for him? Is that actually maybe causing him some issues? And to know that, we'd have to talk to him and also look at some of his other aspects, like how far in front of his body is he hitting the ground? if he's hitting the ground too far, that's actually associated with a lot of impact, which can actually lead to injuries. Okay, so we can go to the next page and look at that. Okay, so here there's two main things, and I'm not going to talk through all of the information because it's a little bit much, but just some of the key points or the key things that we can look at. So here we can look at when he hits the ground, how bent his knee is. Okay, so now when we hit the ground, we have a force. Okay, if our knee is really, really straight, that can create a lot of impact. Okay, and that might actually cause injury. Now, a way to moderate the impact or to deal with the impact is to actually hit the ground with some knee flexion, because then we can distribute the load and we can absorb the load. Okay. So now remember, Aaron had a longer left step, and now what we see is that he's also hitting the ground with his knee more straight. Okay. So to me, that's starting to indicate that he's taking a lot of impact on his left side. And then when we look at how far in front of his body he's hitting on his left and his right side, again, he's hitting further away from his body on his left side than his right side. And actually, if you start to talk to Aaron, he tells you that his injuries are usually on his left side when he gets injured. Okay, so there's some work that we might be able to do here with Aaron, so to decrease his risk of injury and lower his impact force on his left side, working through his biomechanics. Okay, and like I mentioned, there's a lot of information we can get. We can look at the pelvis, see how much someone is bouncing up and down or staying flat on the ground. We can look at how they're moving with their pelvis here, if they're going like this, or how much they're rotating, is if there's a difference between right and left, how that changes. Now imagine if someone is injured. We can use a lot of this information to see where they're at and to track them over time. So it becomes really, really valuable with the work here that we do, both in treating or helping athletes achieve their top performance. And we use a lot of this information as well in research, so we can better understand the way that humans move. So it's really cool. I love doing this stuff every day. All right, so that's enough for the 3D biomechanics. Now we'll take you out onto the track to look at something different. Follow me.
When the day is coming back, this week or next week? Yeah, exactly. This week is coming week. Yeah.
Hi guys, this is Christian. Christian will talk to you guys today about the Optojump system. And we are fortunate enough to also have Aaron as subject again. So he's a superstar. But because we want to make this really exciting for you guys, we'll also have George, our cameraman, who's sitting behind the computer, join into the fun. So George, come on down. And now Christian, off to you.
Kia ora everyone. So we're here in the Optojump station. So as you can see, we have the tracks and we have some lights going on here on the track. So we're gonna measure our differential limb movement. So we're gonna do two tests today. So the visual test, which is gonna measure the reaction time of Aaron in the first test, and then we're gonna have the speed test. We're gonna measure the speed at in the 5 meters. So let's do it. So we're gonna start with the first test, which is the reaction time test. So you want to jump in? Here. So we do like the left foot here. No, left foot here. Here. Yeah. Face me. Here. Left foot here. Right foot here. Yeah. Good. All right. So Aaron is gonna see the light here, and he's gonna get his left foot up and down as fast as he can. Okay? So ready, go. When you see the green line, you're gonna do it up and down as fast as you can. Yeah, 1, 2. So his time was 0.443. So here we have the reaction time of the day. So Aaron is gonna be always here, and our fastest guy was 0.38. You wanna do it again? Sure. All right. So I have 4.404.
Now, to make things interesting, we'll have George as a competition. See if George can be quicker than Aaron in terms of reacting to the light stimulus.
So we're gonna have now a speed contest today. So, everybody? Yeah. Go. Okay, George has 0.428. Wanna do it again?
Yeah, I have to go again.
All right. So now we're gonna do a speed. So we're gonna run these 5 meters, and the sensors are gonna send the speed of Aaron first. Okay? Everything ready? Go. 7.7. So this is the fastest time of the day. So this is meters by second. So the fastest is the more speed that we have. So now George turn. Yep. So George had 5 here. Aaron is the winner of the day.
Rematch. George.
You want to talk about?
Go on. See you.
But Aaron, you go first, and you go first.
All right. Me too. I don't know if I can catch that yet.
Whenever you're ready, go. .8.
Yeah.
Woo!
Slow down.
Got a chance.
There it is.
Yeah. .3.
I'm only good for one.
Who's our winner?
Our winner of the day, Aaron, and the contest between George and Aaron. Aaron. Okay, guys. Let's go to the next station.
All right, team, so that was the Optojump station. So just a quick note on how the technology works. If we go down and look at the gates, so what you don't see here is that there's actually some light that's being sent from this side to the other side. So we have one bar that's sending light and the other bar that's receiving light. So now, anytime that the signal is broken, then the timing light knows that the signal is broken, and it can compute the time from when the light is broken to when it senses it again. Okay. So now that's important for things like, example, when they were running, we could actually calculate the time that they were on the ground and the time it takes from one step to the other step. So then we can look at things like flight time. Okay? And now the first thing that we looked at was a reaction time test. Okay, so by having one foot on one side and one foot at the other, they were responding to the light stimulus. So when the light stimulus came on, the goal of the exercise was to lift your foot as quickly as you could. Okay, so now the computer gave the signal, so the time started, and then as soon as the light beam was sensed on the other side, that's how we were able to record the reaction time. Okay, now try to have a think, why is that important? Okay, when we're playing things like team sports, or say you are the goaler for football or ice hockey or field hockey, you need to be able to respond really quickly to your visual stimulus. If someone's going to throw a puck at you or is going to try to score a goal during a penalty shootout, you need to be able to be really quick on your feet and quick to respond to a visual stimulus. And we can test that here. We can test that in the lab. Okay. We can also see if, for example, if someone gets injured on one side, well, we can compare the reaction time from one side to the other. So that takes a little bit more cognitive process as well. So you're looking at how the body responds, how the muscle responds, but you're also looking at the whole integration of what your eyes see, of what your body senses, and how quickly you can actually respond. So that's pretty cool. All right, the fourth station now. So we're going back into the lab. Thanks, Christian. That was great fun.
Bye-bye.
Cool. Welcome back, team. Now we have Connor.
Hello, everyone.
He's the force strength guy, and he's going to talk to you about all of it. So.
All of it. Okay. Here we go. So my name is Connor McNeil. Welcome to the fourth station here. I am a PhD student here with the University of Waikato, as well as a strength and conditioning coach for some of our teams and athletes that train here. And so just a quick snapshot of the bay, the mount here, and all the awesome facilities and sporting teams that we have access to.
We're coming to you live from this location right here. Really cool.
Awesome. But what I'm actually here to talk to you about is March Madness. So March Madness is a massive basketball tournament. This is kind of the tie-in I've been using all day with our Biomechanics Day. But March Madness is a massive basketball tournament in the U.S. that competes every year. And they just recently crowned the national champion. And so I wanted to tie that in with a bit of vertical jumping. So on the picture here, you can see this basketball athlete is flying through the air. He's jumping through the roof almost. And along the bottom, you can see some of the combine testing, the vertical jumps from one of the recent NBA tryouts that they had. And as you can see, one of the top jumps there is 87 centimeters. It's absolutely astounding that someone can jump that high. And we'll take a look at some of the technology that we have access to here in the lab and how we can maybe use some of that to first analyze a performance like this, see what they're doing mechanically that allows them to perform like that, and as well as what we can use it kind of on a day-to-day basis for monitoring our athletes as well. So just a quick snapshot of the technologies that we're using here and why. So biomechanics is a big part of that is movement, and with athletic movement, we want to look at jumps. So with those jumps, we're going to take a look at the kinematics and the kinetics that we can measure here with the technology in the lab. That includes force, time, velocity, impulse, rate of force development, really cool things that we can dig into and see why an athlete either responds to training the way that they do, or why an athlete performs the way that they do. So it can give us a bit of an insight. And back before all this technology really existed, coaches were able to observe an athlete perform or train, and they were able to make recommendations based on what they saw. And kind of like Kim mentioned earlier with the 3D motion capture, that is one way of doing things, but this technology gives us the ability to make much more precise and accurate decisions based on what we see, as well as capture the entire movement, so we can start to see more clearly what an athlete's doing. And so some of the technology pictured here and that we have here in the lab are the force plates, and we'll talk just a bit more about those here. And we've also got access to gym awares and all kinds of cool stuff that gives us an indication of what an athlete's doing and how they're performing. So with the force plates we have here today, these are Pasco force plates. They're a portable setup, which allows us to move to different testing venues, which is very, very convenient, especially because we're quite mobile with the athletes that we work with here, so different testing locations. Other setups may be embedded in concrete. Those are more sensitive measurements where the vibration of someone walking around might be registered on the device. But with this here, we sacrifice a bit of that precision for the ability to move and test athletes kind of in their natural environment, so that it's a more normal setting for them and they don't feel kind of anxious about doing their best. They can just get right into it in a gym or a lab setting like this. So what we'll do next is have our diehard participant here, Aaron, step on up. And what we'll be doing is recording a couple of counter movement jumps. And the counter movement jump is a test that spans a wide range of athletes, so we can do this with a big number of sports. It's something that most athletes do on a fairly regular basis, so the technique isn't a big variable in terms of performance. It's pretty consistent for us. So we'll pause here, just transition briefly into our testing software. And here we go. If you can see on the TV screen, this is kind of the dashboard. This is the starting place for our testing kind of environment. We've got it set up just to run consistently throughout the day, so we can measure different students. As some of you may know, you've been able to jump and test in this environment. We'll be looking at a counter movement jump, and we'll be calibrating it to Aaron specifically. So we'll get his weight. We'll zero out the force plates, and as you can see, there's a bit of noise in the signal, which is common. So it's important to calibrate this as often as possible and make sure that we get an accurate representation of his performance. So we'll get our two force plates going here. Zero these out. Aaron, would you please step on the plates there? We'll just capture his weight, because once we know his weight, we're able to get a better idea of the forces that he's producing during this counter movement jump. And so we'll go ahead and hit start for right now. And we'll talk you through a bit about what we're going to capture, and then we'll see what Aaron has left in the tank in terms of performances and see what he can do in his jump. So hopefully this fires up pretty soon. Okay, we're off and running. So this is software that we use almost on a daily basis with a lot of our teams based here at the Adams Center. As you can see across the top, there's a lot of stuff that we can break down and look at in very precise detail. These Pasco force plates sample at 1,000 hertz, so we're getting 1,000 data points per second, which gives us a very accurate representation of the forces being produced during this movement. So, like I mentioned, there's a lot of stuff across the top that we can look at. We'll just look at flight height today, which is basically the force plates are estimating the center of mass for Aaron, his acceleration through a jump, and then based on his takeoff velocity, the force plates in the software will be able to calculate how high up in the air he was. So if you're a calculus fan, this is for you. Get a bit of integration here. We'll mix it up. Along this dashboard, we can also see left and right force production. So we've got it calibrated to be able to pick up asymmetries in his movement. So if this was a baseline test for Aaron, we could see where he's at. And then if he does experience injury at some point, we'd be able to understand maybe what's going on. Maybe there's a weakness in his left or his right side, and that would help form his rehabilitation program and hopefully get him back to baseline and back onto the field or track wherever he's at. So, Aaron, how are we doing? About ready?
Yeah. Ready, rock and roll.
Let's get into it then. So we'll have his hands on his hips to kind of standardize our technique. If you're one of these big-time basketball guys, you'll probably be swinging your arms, and you might be doing something like a vertex test, and that would actually give you a little bit more on your jump. You'd be able to jump probably a little higher, but it also increases the variation. So we go hands on the hips to make things a bit more consistent. And this is a counter movement jump, so you'll see him dip, kind of pre-stretch the muscles before he jumps as high as he can. And hopefully the ceiling in here is high enough so he won't go blasting in through the attic, but we'll have to give it a go. We should be all right. Okay, we should be all right. Hopefully he's got enough in the tank, so we'll see how we go. All right, so Aaron, will you please give us just a little bit of just a little jump, kind of a warm-up, and we'll call this your familiarization. So we want to make sure that he's comfortable with the test before we actually get into it. So Aaron, maybe just a little practice jump here before we get into it. There we go. Excellent. So on the screen, what you saw pop up was the force in newtons that he's produced. There's a bit of an imbalance to the left, as you can see on the side there, which is pretty normal, like Kim mentioned earlier. Perfect asymmetry is not very common. Unlikely to see that during testing, but again, if something starts to change over time, these asymmetries get bigger, that might be a red flag for us, an indication that something's going on. And as you can see across the top, we've got a bunch of cool factors that we can look at. Impulse, the amount of force he's produced over time during his jump. Flight height right there was 0.31 meter to 31 centimeters. So you're not quite up to NBA combine testing standards. Hopefully we can get there with your next couple jumps, so we'll get a little bit higher. We'll see. Okay, we'll see. And along the bottom here, you can see the force trace. So this, I'm not sure if it's coming through quite on the camera or not, but you can see the amount of force that he's produced throughout the course of the jump. So the software that we're fortunate enough to have automatically detects what a jump looks like. So it recognizes this shape as a jump, and that allows us to quickly collect data as well as give the athlete feedback. So Aaron, that was a 31 centimeter jump. I think you can do better. What do you think?
I think we got a little bit more in there.
Okay, we think we got a little bit more. So this is his takeoff. This is when he's at the bottom. This little flat spot, if you can see, is when he's actually in the air. And then this spike here is when he hits the ground again. So we'll take a look at another couple jumps here and see how that compares to what he's done already. So hands on hips. Aaron, if you could give us a little bit more here, start to dial it up whenever you're ready.
All right, a little bit more.
All right, excellent. Nice jump, Aaron. So as you can see along our dashboard here, that is a 44 centimeter jump, so a bit of an improvement there from your last one. Excellent. And the nice thing about this software is that in an applied setting, we can create a bit of competition throughout our athletes and teams. So you can quickly say, oh, this person has jumped higher than you. Do you think you can do better? Aaron, do you think you can improve on your best? It's kind of like against your best self. Yeah, okay, this is a process.
And then we'll see George's
self-improvement. And we'll get George in the mix too. George is a bit of a Raiders fan, if you can tell by his cap. That might handicap him a bit. We'll have to see. I don't know. Okay, let's get you one more.
One more, all right.
Yep, and we'll try and beat 44 centimeters, Aaron. So when you're ready, hands on hips, give it everything you got here.
Oh.
Right through the floor. 46, okay, there it is. That's Aaron's test. Well done, well done. Okay, we'll stop that for now. And so that is quite useful. So in an applied setting with this biomechanics lab, we can use this technology to create competition. We'll see what George has. Also, it allows us, like I said, to look at imbalances and asymmetry. So we didn't quite capture it there, but you can see Aaron from left to right went from a 10% imbalance down to a 4% imbalance. So that's a pretty good indication that he's doing fine there. No red flags. So George will get you calibrated into the system. So if you could please step on the plates and just hold still for us.
So guys, this all works based on your Newton's laws of motion. So force equals mass time acceleration. So if we know mass, we know acceleration, we know force, we can all play with those numbers to derive different metrics. So it's really cool stuff.
That's right. Okay, there we go. So quickly, we're wrapping up these Newtonian laws into some awesome jumping exercises and having a bit of fun with it. So, George, if you can go hands on hips for us, please, and then just a little practice jump. There we go. Okay, you can briefly see the newtons there. And on the landing force, what we're looking at over here, so we're seeing peak forces of 2,770 newtons. So you can kind of work backwards to determine how heavy George is and how hard he's hitting the ground. So we're looking at those impact forces. And this is quite interesting when you start to get into sports analysis, looking at how different sports affect it, maybe certain athletes from different sports have certain profiles. So George, if we can get another one here, hands on hips again, just a bit more here, a bit more effort. All right, excellent. Let's see where George is at. Okay, so that's a flight height of 33 centimeters. Get a little bit more on you.
Good one,
okay. 46 is the goal. Can we beat Aaron?
Oh, I'm not feeling confident, but
all right,
we'll give it a go.
He's going to give it a go. All right, team, let's see how he goes here. When you're ready, as high as you can. 38. All right, that's a PB. We'll take that. I think we'll give Aaron the dub, but well competed by both athletes here today. And that just about wraps up what we've done here in the lab. Again, this is kind of an applied setting, so we get to have some fun with it. Get to let athletes be athletes and compete against each other. So if there's any questions online or if Kim has anything else to say, we'll start to wrap up this station. And thanks for participating.
Hope you guys enjoyed that and had a great day. I'd like to thank my awesome team over here that helped with National Biomechanics Day. So from all of us here at the University of Waikato Adams Center for High Performance in Tauranga, New Zealand, we'd like to say get involved with biomechanics. We have lots of fun, and yeah, thanks team.
Yeah.